This lesson is an introduction into natural logs. We're going to use properties of logs to evaluate, condense, and solve equations that use natural logs. So the history of math is actually marked by the discovery of lots of special numbers, like counting numbers, the number 0, negative numbers, pi, and even imaginary numbers. In this lesson, we're going to look at one of the most famous numbers of modern times, the number e. Like pi and I, the number e is denoted by a letter. The number is called the natural base e, or the Euler number, because it was discovered by Leonhard Euler. This guy is pretty amazing and very interesting, so if you wanted to ever read about him, I don't know, maybe you're a dork and you like stuff like this, like me, but this guy is crazy cool. I think you'd be impressed even if you didn't like math with some of the stuff that he could come up with, and half the time, for most of his life actually, I think he was blind. So it's pretty cool that he actually did a lot of computations and stuff in his head. Okay, anyways, to define a natural log, basically the number e, and we literally write e, is approximately 2.74. The number pi, right, is approximately 3.14, and people will often confuse this and think they're variables, but they're not. It's just a number. So when we see a natural logarithm, it's the log with a base of e. That's all that a natural logarithm is. But instead of using log base e, we shorten it up and we say ln instead. So these actually mean the exact same thing, but you're going to typically see this notation, the natural log, written as ln. So the natural log of x is equivalent to log with a base e of x, which means that it's just the log with a base of approximately 2.74. Okay? So don't get confused, it's just a different notation than what we've seen prior to this. So let's talk about some of the properties of logs and the properties of natural logs and how they're related. Now, just to review, log base 10 of 10 is equal to 1. 10 to the first power equals 10, right? Log of 1 is the same as 10 to the 0 power equaling 1. So here, we have log base 10 of 1 is equal to 0. Now, likewise, when we look at natural logs, this is saying the natural log of e. A natural log of e is equal to 1. Over here, the natural log of 1 is equal to 0. What you're actually showing here, if you wanted to write this out, would be log base e of e equals 1. We know that these are inverse operations. They actually cancel each other out and equal 1. So over here, if I were to write this using log base e of 1, this is e to the 0 power equals 1. Now, the same thing goes and applies when we see a log of a product, a log of a quotient, and a log of powers. All three of these rules here apply the same way with a natural log. So the natural log of a product here, x, y, we can split that up and write that as the natural log of x plus the natural log of y, just like this rule here. When we see the natural log of a quotient, x over y, we can take this and change that to the natural log of x minus the natural log of y. And finally, when we have the natural log of x to the n, we can write that power out in front and write this as the product of n times the natural log of x. So we're going to use these properties now and evaluate some logs. So our first up here, this example, the natural log of e. So the natural log of e is like seeing log base e of e. And we know that this is always equal to 1. So even if it was log base 3 of 3, it would equal 1. This is just log base 2.7, about 2.7, of something that's about 2.7 equaling 1. Okay, so the next one, the natural log of 0. Or, I'm sorry, natural log 0. So this is log base e of 0. In other words, e to some number is equal to 0. Well, this is not possible. We can never raise e, which is about 2.7, to any number and get the number 0. So this is not possible. Now, the next question here, we can do this two different ways. We can do it by definition here. We can do log base e of e to the 5th. Remember, these will cancel, and this will leave me with 5. Or I can use it by the property. If I go by our property here, we can pull that 5 out in front, and write that as 5 times the natural log of e. The natural log of e, remember, we evaluated already a couple times. That's going to equal 1, so this is 5 times 1, or just 5. In number 4, let's use our property here. We're going to rewrite this as negative 3 times the natural log of e plus 12 times the natural log of e. Now here, I could simplify the natural log of e to be 1. So this will cancel. The natural log of e is also 1 here. Negative 3 plus 12 is positive 9. I could do this a different way as well. I could have, if I wanted to, write this as the product of e to the negative third times e to the 12th. So the natural log of e to the negative third times e to the 12th. I would add my exponents to get natural log of e to the ninth. And then e to the ninth here, or the natural log of e, cancels, leaving you with just 9. So either way, same thing. On number 5, I'm going to write this as the natural log of e to the negative 24th power. So I always want to see how I can rewrite something in a denominator and bring it to the top. So I'm going to put that and make that e to the negative 24th power. And after this, I'm going to pull that negative 24 out in front. So I have negative 24 times the natural log of e, which means that it simplifies to just negative 24. Okay, now number 6 is, I think, one of the areas where students will make the most mistakes, because they'll look at this and they'll try to cancel things incorrectly. So we always want to make sure we're using only the rules that we've learned, those 3 golden rules. So here, I'm going to first start by taking that 2 and bringing it out in front. So I have 2 times the natural log of e raised to the 6th power over, in the inside of the parentheses here, if I pull that 3 out, 3 times the natural log of e raised to the 4th power. Now, in the inside of the parentheses here, the natural log of e is going to cancel out, and I'm left with 2 to the 6th power all over 3 to the 4th power, because the natural log of e cancels here. So I have 2 to the 6th, which is 64, all over 3 to the 4th, which is 81. So this is going to simplify to 64 over 81. Now, I've seen students who will cancel this or leave this as like 1 over the natural log of e. I don't know, they just see 2 minus 3 and they subtract, so please don't do that. You know, make sure you're just following the rules and simplifying one portion or piece at a time. Now in problems 7 through 9, we're going to condense the expressions. So here, when I see the natural log of 16 minus the natural log of 4, I'm using the same property where I can take that and write that as the quotient of the natural log of 16 over 4. So I simplify here and I get the natural log of 4. I can't go any further to simplify this. I can't evaluate this, so I'm finished here. Number 8. When I look at this, I have the natural log of 3 minus the natural log of x in parentheses, so I'm going to write that as 3 times the natural log of 3 over x plus the natural log of x over 9. So I'm changing both of these into a quotient. And then since I have that 3 here, I'm going to bring that up here, so I'm going to bring that to the power here and write that as the natural log of 3 over x cubed plus the natural log of x over 9. Alright, now I can, since I have the same base, right, the natural log is the same base, I can now take this sum and create a product here. So I have the natural log of 3 over x cubed times x over 9. So now I'm going to simplify here, and if I do that, I have the natural log of 27 over x cubed multiplied by x over 9. So to simplify here, I would cancel here. So I have, let's see, x goes in x cubed twice. I'm sorry, it leaves me with x squared. So I have the natural log of 3 over x squared. And that's as simplified as number 8 would get. Alright, I'd like you to try number 9, and then we're going to move on to solving some log equations. Alright, now in number 10, when you have a natural log equation, you solve it the same way that you would approach any normal log equation. So I want to isolate the log as much as I can in this case. So I would subtract 1 first, so I have negative 2 times the natural log of x equaling negative 5. Now if I divide out that negative, I now have 2 times the natural log of x equaling positive 5. After this, I will now raise this to the 2nd power. So I'll bring that in and I'll have that as natural log of x squared equaling 5. Okay, now I'm stuck, right? So whenever you're stuck, remember our strategy is always to switch forms. So now I'm going to write an exponential. Because I have a log equation, I'm going to write an exponential equation now. Remember, your base here is e. So I have e raised to the 5th power equals x squared. If I want to get x by itself here, I will square root both sides. So I have x equaling positive or negative square root of e to the 5th power. Now I need to check to make sure that I would have a positive argument here. So because the negative would cause a negative argument, I need to throw that one out. So let's toss out that one. So x here is going to equal positive square root of e to the 5th, which you can also write as e to the 5/2. Either one would be totally acceptable. Okay, now in number 11, what I'm going to do first is try to isolate that natural log by dividing out this 3 here so that I have the natural log of x plus 2 equaling 8. Now after this, I'm going to get stuck, right? I can't really do anything to simplify here. I can't do anything other than rewrite and switch this form into an exponential equation. So now I have e to the 8th power, because my base here is e. So e raised to the 8th power equals my argument x plus 2. If I want to get x alone here, I would have to subtract the 2. So I have e to the 8th minus 2 equaling x. So there's my solution here, and that's how you solve some log equations. Now in the next part of the lesson, we're going to look at applications of natural logarithms. Now the number e actually shows up in a lot of things in the real world, such as population growth, global warming, radioactive decay, even investment banking. So like when you try to invest in an account, when they compound the interest on your account, they do that continuously, and they use number e in their calculations. So it has a lot of real world applications, which I think is pretty cool. So we're going to do a couple problems, and you'll need your calculator for this. So let's begin here with number 12, which states that the atmospheric pressure P decreases exponentially with the height above sea level. So in other words, the farther you get above sea level, your air pressure around you will decrease exponentially. So actually this is an exponential decay. Now they give us the equation. They say that the equation relating P and the height h is P equals 14.7 times e to the negative kh, where k is a positive constant. We're supposed to find k when we're given both the pressure and the altitude. So here in part A it says find k if the pressure is 11.9 pounds per square inch at an altitude of 5,000 feet. So right now they're defining for us that P equals 11.9 when our height, our altitude, right, this word just means height, is 5,000 feet. Okay, now I'm going to plug into this equation here, these two values, and I'm going to try to solve for k. So we have 11.9 equaling 14.7 times e to the negative k multiplied by 5,000. Alright, now I'm going to rewrite this just a little bit differently as 14.7 times e to the negative 5,000 k. Okay, now we actually don't have two variables here. We only have one variable, right? We're supposed to find k. Some students will look at this e and think that that's a variable, but it's not. Remember, that's about 2.7. So we do know what that value is, which means it's not a variable. So I can isolate k here by trying to move this 14.7 first. So we have an exponential equation, right? So we'll solve it the same way we would solve normal exponential equations. I'm going to divide by 14.7 first. This will cancel here on the right-hand side, leaving me with 11.9 over 14.7 equaling e to the negative 5,000 k. Now at this point we have an exponential equation where we do not have the same base on both sides, so I can't equate exponents here. So what I do when I run out of something to do, when I get stuck, I switch forms. So I'm going to try to turn this into a natural logarithm. So because I have e here on the right hand side, I'm going to take the natural log on both sides of the equation. Remember, this is log base e now of e to the negative 5,000 k. This will simplify to just being negative 5,000 k on the right hand side. So I've gotten rid of this base e here by taking its inverse function of the natural logarithm. Now on the left hand side I have the natural log of 11.9 over 14.7. Now to get k alone, I need to divide by negative 5,000 on both sides. Okay, so I have k equaling, my exact answer here is the natural log of 11.9 over 14.7, all divided by negative 5,000. Okay, now in my calculator, I'm going to type this in, and I'm going to have this entered as accurately as possible. So you want to make sure that you have your calculator out right now and that you're going to practice doing this with me, because this is an important skill to make sure that you can type this in correctly. Okay, so in your homework or on a test or a quiz, what we need you to do is store your k value. And the directions actually say that above here, store k and round to 3 decimal places. What I want you to always do is box your exact answer here, where I have k equals, and then we're going to show exactly what that is without actually plugging anything into our calculator. I want to show exactly what the k value is, and then I'm going to plug it in my calculator and then show what that is approximately equal to. Okay, so we're going to begin by typing in the natural log of just 11.9 divided by 14.7. Now I'm going to hit enter here, but without clearing this, I'm going to hit divided by negative 5,000. Okay, so this is approximately 4.226 times 10 to the negative 5th power. So 4.226 times 10 to the negative fifth power. Okay, that's what this E and then negative 5 means, 10 to the negative fifth power. So really this is a very small constant. I'd have to move that decimal place 5 units over, so it's a very, very tiny number. Now, what I want to do though is use this same value throughout this problem, right? We found our K value, but we need to make sure that we don't have to type that in every single time. So what we're going to do is store it. So I'm going to hit stow, it's ghetto for store here, and we're going to hit alpha, and I like to call it K, just because it's already that variable, but you could call it anything. So that's why you see the K right above here. That's why I'm hitting alpha K. You could hit anything that you want, though. You could alpha, A, whatever variable you want. But I'm going to store it as K just because we're using K throughout. And I'm going to hit enter. So now that value is stored as my K. So when I move on to the next problem here, where it says find the atmospheric pressure outside an airplane that is flying at an altitude of 22,000 feet. This time, we know our K value. We are missing the atmospheric pressure here. So we're missing our P value. We have a height of 22,000. So we're going to plug that into our calculator here, or into our function here. Our function is P equals 14.7 times E to the negative K times, in this case, 22,000. Okay, now we know the K value, right? We already know this number here. And this was stored as K in our calculator, okay? So let's show you how to put this right into your calculator. Okay, so we have 14.7. Remember, E is not a variable. We already know this number too, so this is something we can type right into our calculator. So we're going to multiply this by E, which is right above the divide key here. So times E, and then we're going to raise this, and we're going to put this in parentheses. Actually, some calculators here, like this one, just automatically did the math type here. Your calculator might not do that, so make sure that you put parentheses. I'm just going to put parentheses in here anyhow, just so that you know that you're multiplying this product here together and you're raising it to this power. So we have negative, and then I'm going to use K again, so alpha K. So now I'm taking the value that I stored and it's automatically going to input that value here. So negative K times 22,000. Okay, so when I hit enter now, this will be the atmospheric pressure in pounds. I think it's per square inch. So we have P equaling 5.801. Okay, now if you guys had not stored K, this decimal would be off by a number that would be significant enough for us to realize that you didn't actually store the value. So you want to make sure that you understand how to store K in your calculator, because at the end, when you finally get your final answer, it will be off by, either hundredths or tenths or some decimal spot. So make sure that you follow the same steps here that we were doing with storing your values. So the last problem that we're going to look at is another real-world application problem. This one is dealing with radioactive decay. So to give you a little bit of background, in July of 2002, National Geographic ran an article about the problems that America faces with its amount of nuclear waste. Currently, the United States has over 77,000 tons of waste that's just buried everywhere. Lots of states. I think Texas has a ton, crazy amounts of nuclear waste, disposed in basically just landfills. Environmentalists talk about how the radioactive material will be dangerous for thousands of years because of its long half-life. And that's what we're going to be looking at and calculating is half-life. In fact, it will take 240,000 years for plutonium-239 to become safe. So when scientists talk about half-life, they're referring to how long it will take for half of a sample to decay. So in the case of nuclear waste, it refers to how long it takes for half of the radioactive material to turn into lead, something safe. Okay? So it's a little disturbing when you think about it. The fact that we have 77,000 tons of waste and growing, and there's nowhere to put it but in the ground, so kind of freaks me out. Okay, so problem 13 here says the mass of a radioactive substance decreases exponentially with time according to this particular equation. Okay, so M is the amount of radioactive substance that is left. So this is your final amount, so M is your final amount, the amount that is left after a certain amount of years. And this, M sub 0, is the initial amount. So it's the initial amount of radioactive substance that you start with. And we're going to multiply by E raised to the negative KT, okay? And K is another positive constant that is unique to the type of radioactive substance. So each type of radioactive substance has its own K value, okay? Okay. So in part A here, it asks us to find K for carbon-14. So this is the type of radioactive substance we're looking at, carbon-14. Now the half-life of carbon-14 is 5,600 years. So in other words, it would take 5,600 years for something to turn into something safe, so for half of it to turn to lead. Okay. Now we're going to assume from above that we're starting with 20 milligrams because it tells us you're going to start with 20 milligrams of radioactive substance. So this is our M sub 0. M sub 0 is 20 milligrams. Now we also know that after 5,600 years, so after time, which would be 5,600, we know that it would reduce to half of its original mass. So M, our final amount, would be 10 milligrams. So that 20 milligrams would turn into 10 milligrams after 5,600 years. It would take that long for it to decay only 10 milligrams. All right, now we're going to find K by plugging these values into our equation. So our final amount, M, is 10. So 10 equals our initial amount, 20, multiplied by e to the negative k multiplied by 5,600. So this is our t value. Now this equation looks exactly like a problem in number 12, and I think these are a little bit more difficult because the information is a lot, I think, harder to interpret. So it ends up looking exactly like a problem that we worked on before, so we're going to solve it the same way. We're going to divide first by 20, so we end up with 1/2. Now, anytime you do a half-life problem and it asks you to figure out the k value or even the amount of time, you're always going to end up with 1/2. For example, if I started with 40 milligrams, my initial amount was 40 milligrams, and I asked for how long it would take to decay to half of its amount, well, then your final amount would be 20 milligrams. So you would start with 20 equaling 40, divide out that 40, and you'd end up with 1/2. So every single time you do a half-life problem, you can actually skip this part where we set up the 10 and the 20 and just go straight to 1/2 equals e to the negative k times 5,600. Okay? All right, now I want to solve and isolate the k. So I'm going to take the natural log on both sides. So here's where it's really useful to write the natural log on both sides, because here, this is going to reduce to just cancel each other out, and we're left with negative 5,600 k equaling on the other side the natural log of 1/2. If I want to isolate k, I'm going to divide now by negative 5,600. So I end up with k equaling the natural log of 1/2 divided by negative 5,600. So again, here's our k value. This is our exact answer. And now we're going to show what we stored k as. So we're going to use our calculator one more time. Okay, so we've got the natural log of 1/2, so you can put 0.5 if you want here, divided by negative 5,600. So I'm going to store k again. Remember, I hit store and then alpha k. And now I have that stored in my k value for my calculator. Okay, so I'm going to write this down, and I think it asks you to round to the third decimal spot, so this would be 1.238 times 10 to the negative fourth. Okay? All right, now when we work on the next problem, it asks you to find the exact same thing. Find the k if the initial amount of radioactive substance was 30 milligrams. So here, we're starting with 30 milligrams, right? That's our M sub 0. Well, our final amount for half-life would be 15, okay? And it would take 5,600 years in order for it to reduce to 15 milligrams. So we plug in 15 here for M equals 30 times e to the negative k times 5,600. Now, if we solve for k again, I would divide out the 30, and look at this, I end up with 1/2. This is exactly what I was just talking about above. So we have 1/2 equals e to the negative 5,600k. Again, I would take the natural log on both sides and I would solve. Well, we already know what that equals, right? It's the same as this. We have the exact same equation here that we're solving, and that's because the k value, no matter what you start with, it's unique to the type of substance. So k value is unique to the type of substance. It won't change no matter how much of the initial amount you have. So if you had 30 grams or 30 milligrams or 10,000, it wouldn't change the amount of time it would take for it to decay to half. The k value is the same when it's carbon-14. It doesn't matter how much you start with. Now, if it's a different element, then it would take, it has a different k value, okay? Or if it's a different, radioactive substance, then it has a different k value. Okay, now for our last problem here, it says a bone is found with 30% of its carbon-14 remaining. How old is the bone? Now all we really need to know here is our K value, okay, which we already have saved. It was stored above. And the question here is asking how old is the bone. So T is what we're missing, which means we should know M sub 0, and we should also know our final amount, M. Now, if you notice, they didn't actually tell us what you started with here. All it says is that the bone is left with 30% of its carbon-14 remaining. Now, remember, it doesn't matter how much you initially have. Since we have 30% remaining, that means that we have 3/10 here on the left-hand side of our equation, equaling e to the negative kt. Okay, and it's similar, right, to what we solved for here. Remember, half-life ended up looking like this. Okay, now in this case, we don't have half, we have 30%. In other words, 3/10, right, 3/10. So if I had started with, and I think I need to show you exactly what I mean, but let's say I had started with 10 milligrams. Well, if 30% is remaining, then that would mean I'd have 3 milligrams left, right? And when I plug that into the equation here, M equaling M sub 0 times e to the negative kt. If I plug in the 3 and the 10 here, I have 3 equals 10 times e to the negative kt. When I divide out that 10 to try to solve and isolate k, I end up with 3/10 here. Okay, so this is why I can skip here to this type of, or to this equation here. So if it had said 40%, for 40%, we know it's 4 over 10 equals e to the negative kt. If it said 50%, then that would be half-life, right? And that would equal 1/2, and so on. So it's not meant to be tricky. Basically, you just have to understand that the relationship here on the left-hand side is showing what's remaining, right, in comparison to the original amount. So it would be 30%, 3/10. Okay? All right, so if we want to solve for t here, let me erase everything else here. If we want to solve for t, we want to isolate here, and we're going to take the natural log again on both sides. So we have the natural log of 3/10 equaling, on the other side, this is going to cancel, leaving me with negative kt. Remember, we already know what the k value is, so I can divide by negative k here to isolate t. So t is going to equal the natural log of 3/10 divided by negative k. So I'm going to take my calculator here, and I have that k value stored already. Let's move this over to the other side. So I have the natural log of 3/10, or 0.3, whatever you want to put in there, and divided by negative k. I'm going to put this in parentheses, negative alpha k, and this would give me my time period, 9,727 years. So it's 9,727 years old. It's a pretty old bone. Okay? Alright, that's the end of the lesson. Make sure you come to class tomorrow asking any questions. I know that this application stuff isn't easy, so please make sure you're asking for help. Alright, nice job. We'll see you tomorrow.